organic coating or inorganic coating, it will keep the chlorides away for a certain time. Okay? Remember that, it's for a certain time. You're buying time basically. You're not going to get infinite time, but you're buying time. So there's quite a lot of chemistry involved in getting the coatings. There's a lot of people working on that as well, surface coatings. Surface coating is a great thing if you ask me. I like surface coating to resurface, become very dominant in the future. One, for the reason you can get the finish that designers require. Making concrete for that finish is not desirable because they're going to do that by unsustainable means, by either increasing the cement, using particular kind of cement, going further away from this, buying aggregates from around the world to do it, and making the technology so focused on concrete. I would avoid that. I would make the concrete as good as I can and apply a surface coating in the way they want it. That solves the job in two ways. That surface coating should do more than one thing. It's a chemical environment. So it can give you the good finish. It can protect and keep the chlorides away. Anything else? So the surface coating can be designed anyway. There are other reasons as well. But the best reason, I think, it can keep the moisture in the concrete, in the fresh concrete, locked in so that the concrete has the best chance to cure for a longer period. That curing is significant. If you can cure the concrete 2 years in a perfect environment and then expose it, you're going to get a much better service life. 2 years is an impossible task for a fast-paced, fast-changing industry. But you can buy that 2 years if you put a coating on it. Okay? The existing coating systems and the coating methods may need to evolve in the future. It probably will have to do more than one job. But then you're taking medicines which can do more than one job these days. I'm sure the coating technology can evolve as well. Okay? So for those who are working in that area, just remember that the coatings will, I believe the coatings will start to take its predominance in the future. You do know that now they use what is it called? Curing compound on the surface of, yeah? So it is to leave, so it's a cast concrete and it's to leave the moisture within to cure it better and also to avoid any surface moisture evaporation. So that's widely used, or is it? Okay. The cost will come down. The more people working on an area, the cost will fall. That's where you need to be starting to work with the chemists and the physicists, to be honest. Because they can create surface tension in the way you want it. And they might actually look at the whole picture as a surface tension and an interface issue. It's weird when you read their papers. I don't understand any of it, but I know you're talking about chlorides. Right, so that's about chlorides. We have 5 minutes to finish. Okay, no, I'm going to give a task for them in a minute. So the chloride content, which is referred to as chloride threshold, in which the corrosion will initiate, is a very debatable topic. There was a Ryland committee on the chloride threshold, even they couldn't agree really anything particular. The reason is the environmental factors have a large role to play. The type of cement has a large role to play. The steel and the surface condition of the steel has a role to play. So if you use a rounded steel, it might corrode at a different time than the torque steel that you buy, the twisty steel that you buy. And if you're in any means of modifying the surface of the steel ultrasonically or any form of surface hydration, surface hardness properties, you might get a different chloride threshold. Okay? And it's very difficult to predict it. And this is why the committee couldn't really agree on saying this is the threshold. And the intention of the Ryland committee was to say this is the starting threshold, but it can go up to here, but you should be calculating from a particular value. I don't think they agreed anything. But needless to say, we have noted structures that corrodes at 0.2, which is very, very low by weight of cement, to structures that are still happily sitting there with 1% by weight of cement, chlorides in it. Depends. I don't know the answer to it. So chloride threshold is one thing. We're going to assume the chloride threshold for most of the mathematical work. And we're going to say that assumed value, the moment it exceeds, is considered as failure, which is also not true, because once it exceeds, then it goes to initiation of corrosion, then it goes to propagation, then it goes to section loss, then it fails. We're going to ignore all of that and just say service life is when the initiation happens. It's a very conservative way, but it's an easier way to calculate. If you're into corrosion, there's a lot of people working on what's called probabilistic method. Those are structural engineers. And there's a lot of people working on the steel corrosion interface. I guess one of your students is working. There is a Ryland committee, the same committee which did the chloride threshold has now moved on to, because they realized steel concrete interface has a lot to answer, so they moved on to that. So keep an eye, if you're researching, keep an eye on what the RILAM is one of the research organizations. Keep an eye on what their committees are. Because their committee output is a book quite often, or a conference, and RILAM proceedings. Quite a good summarized version of state of the art. Okay, that's a good way to start your learning. We won't go too much into corrosion, but in most of our approximation work for whole life management, we try to keep it from corroding. Because once it corrodes, the American things will assume 6 years after initiation to be the service life. But corrosion means you need to have an anode and a cathode. It's nothing but a battery. It's the same as your battery. So you need an anode and a cathode. They need to be electrically connected. They need to be ionically connected. If you break one of them, you break the whole thing. And the fundamental requirement for corrosion is you need to have water, you need to have oxygen, and you need to have a substance that can initiate catalyst. So the pH change is a good catalyst. Chlorides are a good catalyst. But if you cut either water or oxygen, you've done the job. Easier said. If you make concrete which is electrically resistive, very resistive concrete, but has a loose pore structure, corrosion may initiate here, okay, but it will fail to transfer the ions from there to here, okay, and that's enough to cut the circuit. So corrosion will be very localized. It'll start, but it'll stop. But the problem is, it might actually have the anode here and the cathode right next to it. And that's the nature of corrosion. Why is the steel trying to corrode? Quite annoying. Why is it trying to corrode? I asked too many questions. What in the steel is forcing it to corrode? When you put steel outside in the normal environment, here it's not normal, you're too close to the sea. But anyway, if you keep steel outside anywhere, it will corrode, right? But why? Which is? All steel is trying to do is to go back where it was in the first place. You took it out, you heated it to bring it to a high energy state into the steel that you want to use it. So steel is just trying to walk its way back. Engineering is about using the material in that duration before it goes back. In saying that, I'm quite aware that I'm trying to use that material for a specific life that it will give me before it will go back. So it will go back. If you leave a structure to be, it will disintegrate to bits, it will completely evaporate and disappear in time. Concrete will start to fall initially, steel will corrode, steel will expand and go and dissipate into the water, it'll evaporate nearly. And same with concrete, it'll break down, weathering will bring it down into the finest and the lowest particles that it once was. Thousands of years maybe, but it'll take. So steel's trying to go back to its low energy state. It's a happy state for it to be. We want to keep it at a higher state only for a certain amount of time. And after that it will go back. Okay? So I'm going to stop the lecturing part of it there, but I do have an assignment for you. Okay? Assignment is very simple. Simple, but I need to read. Where do you search? Do you search in Google? Do you have any other searching platform where you want to find an answer? Don't go to libraries, just use Google on your phone. Find the youngest structure that has corroded due to a material related issue, concrete structure around you. Okay? Find the youngest structure. And while you're doing it, also figure out why did it fail? Because obviously failure is what most people report as failure. And also figure out why did it fail? Can you pinpoint one reason to say it failed because? So bring it out tomorrow and we will have a chat to see if people have found different things. Okay? I'm assuming that most of you are going to find the same structure if you're going to Google. That's why I asked what search platform are you going to use. While that, also look at the structures that have failed recently around here. In the south or north. You were saying in Calcutta there was a failure, wasn't it? During Asian Games there was a failure in Delhi as well. One of the bridge collapsed. Okay. I'm not looking at structural failures, okay? I'm looking at failure due to materials. Okay. That's the youngest structure I'm looking for. Okay? That's it. Will stop here. I will go through a couple of more deteriorations tomorrow. Other things to watch out for. The way I'm giving the lecture is to say what the deterioration mechanism is, what the factors are, and how can you control. Okay. The funny thing is, you do know the answer. You have the answer within. I'm trying to refine it and give it a structure so that you can start thinking in that direction. Quite often, with experience, you would know the answers anyway. And if I don't know it, I'm trying to get it off you at the same time. So we'll follow the same format. I will ask a lot of annoying questions. And tomorrow we will start to look at testing. Because durability is one thing where you can prescribe it to the best and make a best concrete. But everybody has to take your word. And that's not good enough. For compliance and for any other things, that's not good enough. So we need to find a way of testing them, because what's the way you test concrete now? What's the most common test that you do for concrete? Compressive strength, right? Okay. Why is that so popular? It is. That's the thing. Testing has to be easy. I did show in my research that we focus on non-destructive testing on the surface and all of it. It's not easy, it's not cheap, therefore it will never fly the flag. But hey, university requires few things, we give them what they need. But the testing has to be easy, and it has to be for the function that your concrete will perform. If you're going to put that concrete in water, you'll need to be looking at those kind of tests, which will either give it the strength to keep the water away, or give it a strength that the corrosion doesn't initiate. Okay? So tomorrow we will look at some of the deterioration and we move to testing. Okay? I'm going to make all of you into test developers. There's a lot of money in it actually. Testing is a big area. There's quite a bit of money involved in it. Okay, have a good day.